In this video, I'm going to show you how you can use Pid Control for robotics. And most often this is applied for line following, but you can also use it for wall following or moving your robot straight. Before I go any further, make sure you like this video and subscribe to the channel. So in line following, for example, if we have a line, then our goal is to keep the color sensor in the middle of the black part and the white part of the line. But what can happen is the color sensor can be on the white part of the line, or it can be fully on the black part of the line, or it can be somewhere in between these two ranges. But ideally, we want the color sensor to be guided toward the middle so that it can continue moving straight on the line where the black and the white meet. And so the goal of Pid Control is to find the optimal path for the color sensor to adjust to bring it closer to the line no matter where it is, whether it's on the white or it's on the black. And so PID can be broken down into proportional, integral, and derivative. And each of these is assigned a constant. So for proportional there's Kp, for integral there's Ki, and for derivative there's Kd. And what these three values do is they multiply by the factor that we determine for the proportional, integral, and derivative part, which I'll explain. And they adjust the values of that so that we don't change the speed too much. So these three are all going to multiply by the error that we determine from the proportional error, the integral error, and the derivative error. And then we're going to sum them all up, and that's going to give us the speed change. And we add the speed change to the baseline speed, and that allows us to change the speeds of the motors that are moving. And by using this value here, speed change, we're able to guide the color sensor closer to the center of the line. And so generally speaking, all of these values are less than 1 because we don't want to increase any of these values. And as we're going to see, the proportional, integral, and derivative values can become very large numbers. And so sometimes these constants end up becoming very small. And so what I'm going to do now is explain what each of these terms mean. So to start off, proportional would generate a graph like this if we were to plot where the color sensor is over time. So this would be the center of the line, or the target that we want to reach. And what I'm going to plot is the error, or the distance from the center of the line, and we're going to do that over time. And what's going to happen is if the robot starts on the white part of the line, like over here, then the error will be very large, and it will be a positive error. And as we run the program, we want to aim to reduce this proportional, and once we reach the middle of the line, something else might happen, and the robot might all of a sudden be on the black part. And so the error is going to continue increasing, but then we might make an adjustment, and the error might end up eventually becoming 0. And so the proportional part of this would look at the error, and that would be the distance from the location of the color sensor to the target. And so over here, when we start the program, we have a very large error. Whereas when we're closer to the target, the error is smaller because the distance between the location of the color sensor and the middle of the line is smaller. So here, the proportional part would be larger, whereas here it would be smaller. And the same would apply when we're on black. So over here, the proportional part would be larger than the proportional part over here because the distance away from the line is larger. And now the integral component will look like this. So same thing, we have error here, and we have time. And if we have the same graph as I drew earlier, the integral is the area under the curve. So here we would have this area, and then as we proceed with time, all this area accumulates. And then when we cross the black, the previous area that we had begins to eliminate because this area here is negative and this area here is positive. So the goal of the integral is to make the net area 0. So if we were to start on white and we accumulate all this positive error here, the robot would end up steering toward the black in order to negate that error and make the overall error 0. And this is especially useful if there are any consistent errors that are within your program, and that could be due to the mechanical design of your robot or programmatic design. And lastly, there's the derivative. And for the derivative, I'm going to do the same thing. I'm going to plot error over time, and I'm going to have the same graph as I had earlier, except this time the derivative measures the change of the error. So here the error change is almost 0 because if I were to draw a line, which is called the slope would be 0. Whereas over here, this slope is steeper. This line that I've drawn here is steeper, so this would have a larger derivative. And here, again, it's a small derivative, and here it's become large. So what the derivative part of this does is it increases the speed change if it's seeing that it needs a large change in error in order to reach the center of the line. So over here, the derivative part would be larger, so the speed change would have a larger value here, whereas over here, the derivative is almost zero, so the speed change would be lower. So when you individually multiply these three errors with Kp, Ki, and Kd and sum them up, you end up with speed change, which is the amount that the robot is going to change its speed by. And so when it comes to line following applications, many people aim to have a PID line follower, but realistically from my experience, you generally don't need the integral part. And this is because the robot generally does not have a hard time moving away from the black. Once it's on the black part of this line, it tends to move out. But at the same time, it does have a lot of trouble coming from the white back to the center. And this is because in competitive environments, the target value that you're trying to aim for is usually greater than 50. And when the target is greater than 50, that means that you're going to have smaller errors whenever you're on white and larger errors when you're on black. And that means the adjustment for getting off of black is always going to be greater. And so this means that realistically an integral graph for a line follower with robotics would look something like this. And this would mean that the integral is always going to be positive over time, because it's never crossing this axis. It may cross a little bit, but the net result would be a positive error. And so this would lead your integral to accumulate over time, and that would cause your robot to have to adjust for this by changing either the proportional or the derivative part of this program, and that would lead to your line follower being very jerky. And if you have a jerky line follower, it's going to end up being inaccurate. So the best solution that I have to fix this is, if you're trying to do a PID line follower, just use the P and the D components, because you don't need the integral. And so here is an implementation that I've shown for Spike, and if you notice, you'll see that I've set the Ki value to 0 in my Spike program, and I've shown the code here in case you want to adapt it to be used for wall following or keeping the robot straight, but for line following, I would strongly recommend that you leave this Ki at 0 and only modify the Kd and Kp values.